To construct a square root means you have something like square root of 7, and the goal is to make a line segment whose length is the square root of 7. There are several ways to do this. One way would be to make a right triangle that has a 1 and a 1 as its two legs, making the hypotenuse the square root of 2. Then if I made a perpendicular line perpendicular to this hypotenuse, that's length was also 1, then this other hypotenuse would be the square root of 1 squared plus square root of 2 squared, which would be the square root of 1 plus 2, which would be the square root of 3. And then if I made another line segment here, that's length is 1, again this is a right angle, then this new triangle here would have a hypotenuse of the square root of 1 squared plus square root of 3 squared, which is the square root of 1 plus 3, which is the square root of 4, which is 2. And if I keep doing this, square root of 5, square root of 6, square root of 7. So all these small size are 1, and this spiral thing would enable me to create a line segment that has the length the square root of 7. But an easier way to do this would be to make a line segment that's length is 7 and another line segment whose length is 1. So the thing I want to get the square root of is the length of that first segment. Then we find the midpoint of this segment, which is over here, and we use it to create a semicircle. And then we draw a perpendicular line from the place where the 7 line segment and the 1 line segment share that point. And this line segment will have length the square root of 7. And the reason that is that if I draw in these two lines, there's a rule in math that anytime you have a semicircle and you have a point on the semicircle and you make a triangle with the endpoints of the diameter as two of the vertices and the point on the semicircle is the third vertex, that will always be a right angle. There's also a rule in math that if you have a right triangle and you draw an altitude to the hypotenuse, there's a relationship between the length of the altitude and the two pieces of the hypotenuse. That relationship is a over x equals x over b, or x squared equals ab, or x equals square root of ab. We call this, when this happens, it's called the geometric mean. X is the geometric mean between a and b. This rule is true because there's a lot of similar triangles in this picture. So we can see the x and the a are, the x corresponds with this angle, and the a corresponds with this other angle in the left-hand side triangle, and in the other triangle, the x and b are kind of reversed. Anyway, back to this picture. So if I call this x, I can say that 7 over x equals x over 1, or x squared equals 7, or x equals the square root of 7. So that's a way of making a length that's got some square root that you want. Sometimes there are some sneaky ways, like if I want to make the square root of 13, I could go 13 and 1. This is the easiest way, and that would be the square root of 13. Or I could even get fancy. Actually, sorry about that. 13 is not a good example for that. Better example is the square root of 15. So I could make 15 and 1, and this thing will be the square root of 15. Or I could go 5 and 3, because here we have the geometric mean is the square root of 5 times 3, also square root of 15. So this idea actually works with paper folding also. We can extend it. So if I want the square root of 7 on a piece of graph paper, I can make a point here at 7, 0, and another point at 8, 0. And this point here is at 0, 0. And my goal is to find the intersection of the semicircle with this. Here's the line that I want to find the intersection of the semicircle that would be over here with that line. So the way I can do that is if I fold the 8, 0 onto the 0, 0, I'll get this sort of midpoint here, this 4, 0 point. And now the goal is to find the intersection of the semicircle that would have 4, 0 as its 4, 0 as its center, and 8, 0 would be a point on it. So this is where axiom 5 comes in from the last video. If I find a fold that puts 8, 0 onto this line so that the fold goes through this other point, that fold would look something like this. So I'm folding P onto the line that is ending up somewhere over there. I'll just call it P prime. And if I make that fold, sorry, I should go back. So first I actually make the folds. Then I try to see when I fold P onto this line L, it makes the fold, but I don't really know where P went. So if I want to see where P went, I could make another fold. This time we use axiom 4. I make a line on the fold, and then I fold that line onto itself so that it goes through P. And what that actually tells me, this point here is real important, because this is the point that P got folded to create that first fold. Well, this line segment here, make it blue, will be the square root of 7, because basically what you've accomplished, what that fold accomplishes, or the place that you have to fold P onto, is the intersection of the circle that has the center, which is the point that you want the fold to go through, and also goes through that other point. So paper folding enables me to create the square root of 7 that way.